everybody. So for the second part of today's lecture, we're going to go ahead and start chapter 7, which is about alkynes and the reactions of alkynes. So a little bit of, game plan for this chapter, a little bit about the game plan. So the first thing we'll do is just introduce alkynes as the functional group, look at the general properties of alkynes in terms of bonding and hybridization, and then we will do nomenclature of alkynes. Then we'll jump into the reactions of alkynes, and we'll see for the most part, a lot of the reactions will be familiar to us because they parallel the reactions of alkenes. But we'll see the main difference between alkynes and alkenes is the number of pi bonds. So alkynes have 2 pi bonds, whereas alkenes only had 1. So some of our reactions will be, again, as I said, parallel to alkene reactions, they can just happen twice. Okay, so let's first introduce the alkynes as a functional group. Okay, so there's our alkyne. So let's remember what the hybridization of the carbon and the triple bond is. So hopefully we remember that hybridization is sp. That gives us a 180-degree bond angle and linear geometry. And then in terms of the carbon-carbon triple bond, we should recall that that's made up of 2 pi bonds and 1 sigma bond. Okay, and so the fact that there's 2 pi bonds means there's 2 sources of nucleophilic electrons that can react under electrophilic addition reactions, which are the reactions that we learned of alkenes. Okay, so before we talk formally about the naming, I want to talk about some classifications of alkynes. And the classifications are going to be based on the number of hydrogens attached to the carbons of the carbon-carbon triple bond. So if we were to have 0 or 1 or 2 hydrogens attached, that would change the classification. So if there were no carbons attached to the carbons of the alkynes, in other words, both of these positions are hydrogens, then we would classify this as, well, just ethyne. It's not a classification, but instead just the name of the molecule. Okay, when we have 1 hydrogen that's attached to the carbons of the carbon-carbon triple bond, we call this a terminal alkyne. Terminal alkyne. Okay, and it's called terminal because the only way to get that proton there is if the alkyne terminates the carbon chain. And these end up being super important in this chapter because of the acidity of a hydrogen on an sp hybridized carbon. And so we'll see one of the first reactions of alkynes involves that proton. Okay, and then lastly, we have the internal alkyne. Okay, so if the alkyne is in this middle of our carbon chain, it's called internal. All right, so let's go ahead and talk about nomenclature of alkynes, and then we'll come back and consider the reactions of alkynes. Okay, so basically the rules for naming alkynes parallel alkenes, except for we're going to have the YNE ending for alkyne. So we're going to number the longest carbon chain that contains the triple bond. We want to give the triple bond carbon the lowest possible numbers. We'll indicate the position of the triple bond in the written name by the lower number. And then if we have molecules that have more than 1 alkyne, we will call those diines, triines, etc. Okay, so these first 3 examples are just when we have just alkynes and no other functional groups. On the next page, we'll think about if we have both alkynes and alkenes present in the same molecule. Okay, so for our first example here, we're going to start numbering from the right to give the carbons of the alkyne the lowest number. And then in the written name, again, all the substituent information comes out front. So 6-methyl, and then we have hept for a 7-carbon chain, and then 1 for the position of the alkyne. And notice this YNE ending for our alkyne. Okay, and then remember back in the alkenes chapter, we actually had 2 places that we could put that name. Same thing is true here. So we could have 6-methyl hept1-ine or 6-methyl1-heptyne, and either of these would be fine. Okay, and one thing that I will mention is, since our alkynes have sp hybridization and 180-degree bond angles, there's no stereochem that we have to consider about. There's no cis-trans, no EZ, no RS, at least as it relates to the 2 carbons of the alkyne. Okay, so then in our next example, we have 2 possible numbering schemes. And the alkyne is right in the middle of the molecule, so then we're going to defer to the position of the substituents. And so if we number from the right, that will give us a lower set of numbers to our substituents overall. Okay, because we have 2 methyl groups at carbon 2 and 1 at carbon 5. So that gives us the lowest set of numbers in that way. So this molecule would be 2,2,5, tri for 3, trimethyl, and then hex for the 6-carbon chain, 3-ine. Okay, and then Lastly, here's an example of a diene where we have two alkynes in the same molecule. So we're going to want to give the lowest set of numbers to the alkynes overall. We would use substituents as a tiebreaker there. In this case, we don't have a tie. So we have alkynes at carbons 1 and 4. And so substituent information out front. So 3-isopropyl. And then hexa, notice how we're keeping the A of hexane. So hexa 1,1,4 diene. Okay, so just notice that we're keeping that A in hexa 1,4 diene, just like when we named dienes back in chapter 6. Okay, so on the next page I have the molecules that have alkenes and alkynes. And so all I wanted to point out is that alkenes are slightly higher in priority than alkynes, as we can see. So we'll see generally alkenes take priorities, but they're in terms of numbering and naming, but there are a few exceptions to that, as we'll see. Okay, so these molecules we're going to number or name are called ene-ines, so molecules with both alkenes and alkynes. And so as I just mentioned, alkene is a higher priority, meaning it should have the lower number, unless the alkyne has a lower initial number or there are substituents present in the molecule that are closer to the alkyne. So in our first example, we can see that our alkene and our alkyne are on the two far ends. And so for that reason, we would start numbering from the left to give the alkene the lowest number. Okay, so we have a 9-carbon chain. Now, how are we going to indicate in the written name that we have an alkene and an alkyne? Okay, so here we have non for 9 carbons, and now we have to put the numbers in the middle of our root name, okay, because we're going to have a number for the alkene and for the alkyne, so we have to number in this way. Okay, so it'd be non 1-en for the alkene, -8 YNE-ine for the alkyne. So it's always going to be the ene before the ine, and the numbers have to directly precede the functional group they're talking about. Okay, so let's go ahead and look at our next example. Okay, so here's an example that basically highlights the second exception we have there. So we have an alkene and an alkyne, but the alkyne would have a lower initial number if we started counting from the left. Okay, and so for that reason, we're going to start numbering from the left. Okay, and so now we have an easy geometry thing to deal with. That alkene is of E geometry, so that will come out front, and it'll be E pent for 5 carbons, and then it's always ene before ine, so it'd be 3-ene 1-ine. Okay, so it doesn't matter if the alkene or the alkyne had the lower number, it's always ene before ine in the written name. Okay, and so this next example, I'm actually going to skip the next one and go to the bottom one because that's going to highlight the other example or the other exception we had. Substituents are present and closer to the alkyne. Okay, so in this example, we have the alkene at the alkyne at the two ends, but notice how that dimethyl group is closer to the alkyne. And so that's going to shift the priority over to the alkyne in terms of numbering. Okay, so we still have a 9-carbon chain, and we're numbering now from the other direction than we were from our first example. So this is 4,4-dimethyl. And then we have non for 9 carbons, 8-ene, 1-ine. Okay, our last example now is going to be an example of a diene and an ine. So let's figure out how we're going to do that. So the first thing is we have an easy geometry thing to deal with. And notice how that central alkene, this alkene right here, is right in the middle. And so since it's right in the middle, we're going to default to our rule that the alkene is generally higher in priority. So for that reason, we're going to start numbering from the right. Okay, so now in the written name, we'll put out our substituent information. We have E. I don't know why this is all deleting. Try to draw one more time. Okay, so we have E. All right, and then hexa 1,3-diene. Oh, I see why, because we're highlighting. Hello. All right, so let me do that again. So we're going to number from the right. Okay, so now in the written name, we have E hexa 1,3-diene. Notice how we don't have the E there. 5-ine. Okay, but we do keep this A from the parent chain hexane. Okay, so it's E hexa 1,3-diene for the 2 dienes and then 5-ine. Okay, I'm going to pause here and I'm going to come back in just 1 second and we'll talk about the reactions of alkynes. All right, so the last quick thing that I want to introduce today is basically to reconsider the acid-base properties of terminal alkynes and think about how we can utilize that in some sort of reaction. Okay, so what we're going to be talking about today is acetylide anions. Okay, so what is an acetylide? So acetylide is the conjugate base of a terminal alkyne. So what we have to remember is the acid-base properties of that proton. So how acidic was that proton? Okay, so what we could remember is its pKa is roughly 25. So there are actually several different bases we could use to deprotonate that position. So the most common one is NH2 minus. Okay, so the reaction that we're going to perform is with NaNH2. This is called sodium amide, which is an unfortunate name because you would all recognize that that's not an amide, but that's just the way that it is. Okay, so the base in this reaction is going to be NH2 minus. We can write our acid-base reaction. Okay, it's the product of this reaction that is the acetylide anion. Okay, our spectator ion is sodium, and we've generated ammonia as our conjugate acid. Okay, so the pKa of ammonia is roughly 34, 35, and so that means the equilibrium of this acid-base reaction would lie towards the right. Okay, and it's this species right here, which we're going to spend some time talking about. This is the acetylide anion. Okay, and so what is important about the acetylide anion is it is nucleophilic on carbon. Okay, so let me just draw its structure again right here. Okay, so this carbon is nucleophilic. Okay, so it's a nucleophilic at carbon. We actually haven't seen any examples of a carbon-based nucleophile yet, right? We've seen water, we've seen halides. What else have we seen? We've seen, I guess that's kind of it for now. But now we're seeing a carbon-based nucleophile. And so why this is important is because if we react this with a carbon-based electrophile, we can form carbon-carbon bonds. And in this semester, this is one of the only carbon-carbon bond forming reactions that we're going to see. Second semester organic focuses heavily on carbon-carbon bond forming reactions. Okay, so what we're going to talk about is something called acetylide substitution. Okay, and so what we're doing in acetylide substitution is we are using a carbon-based nucleophile with a carbon-based electrophile to form a carbon-carbon bond. Okay, so we'll generate our acetylide as we just talked about a minute ago. Yes, we have acetylide. And now what are the electrophiles that we are going to react with? Okay, so they are generally alkyl halides. Okay, and so in this case, X could equal chlorine or bromine or iodide. Okay, and this reaction is the best if the R group attached to the halide is methyl primary or maybe even secondary. Okay, so let me draw the mechanism for this. Okay, so here's, if we thought about our alkyl halide and where it's electrophilic, so remember that the halogens are electronegative and they pull electron density towards them. And so we have a polar carbon halogen bond. Okay, so that makes that carbon electrophilic, and then we would break the carbon-X bond. Okay, so we have just made a new carbon-carbon bond. So the product of our reaction would look like this. Okay, maybe I'll make this R prime so we can identify it there. And then we have X minus, which we call the leaving group. Okay, so this R prime group is now over here, and we have generated this new carbon-carbon bond. Okay, and so in our class, I can't stress this enough, this ends up being super important reaction because it's really one of the only ways we have to make carbon-carbon bonds in this semester. Okay, so let me go through two examples of this. Oh, and one thing I will mention is this mechanism that we're seeing here is one of the main reactions in chapter 9. It's called an SN2 reaction. Okay, and so we'll talk a lot about the stereochemistry and the ins and outs of this mechanism to a lot of detail in chapter 9. For now, we need to be able to predict the products of these acetylide substitution reactions. Okay, so in both of these examples, I'm going to go ahead and go through the deprotonation and kind of think about this in a stepwise fashion. Okay, so how could we write this? So NaNH2 and NH3, okay, so we're using NH3 in this case as a solvent. Okay, so that generates acetylide. And then to that acetylide, I'm going to add an alkyl halide, something like methyl iodide, for example. Okay, so the intermediate of this reaction then would be the acetylide anion. Okay, and then it's going to react with methyl iodide. So we could draw the mechanism for that step. If my acetylide anion attack that carbon, and then that iodide, the leaving group leaves. So we've just made a new carbon-carbon bond between the carbon of acetylide and the carbon of our methyl iodide. Okay, so let's predict the products then of that mechanistic step. Okay, and there is our new carbon-carbon bond. We've elongated the carbon chain by 1 carbon, but we could vary, that alkyl halide for whatever we want it to be. And so we could have longer carbon chains to, make longer, to elongate the chain in different ways. Okay, so let's look at one more example of that, and this will be our last example of lecture today. Okay, so here's our terminal alkyne. And again, we're going to react this to first generate the acetylide anion. So this is going to be NaNH2 and NH3. And then in step 2, we're going to use this primary alkyl bromide. So I would probably recommend counting your carbon chains. And I'm doing this not for naming, but instead to keep track of what my products are going to be. So I'm going to generate the acetylide anion at carbon 4. Okay, and that carbon 4 is going to react with carbon 5 of my alkyl halide. Okay, and so I numbered it in that way, so we'll have continuous numbering in the product. So here's my mechanism. Carbon nucleophile attacks the carbon electrophile, and the leaving group bromide leaves. So the product of this reaction then is going to be a 7-carbon chain. Okay, so let's go ahead and count the carbons of our products to make sure we did that appropriately. So we can see a new carbon-carbon bond between carbon 4 and carbon 5. So here's our new CC bond. Okay, so again, I'll reiterate one more time that this ends up being a really important reaction because we're generating a new carbon-carbon bond, and we're not going to have too many ways to do that this semester. So you want to keep track of this and make sure you really understand what's going on in each of these steps. Okay, so what we're going to do in lecture on Wednesday is I'm going to talk about ways to prepare alkynes using reactions from chapter 6. And then after we've talked about that, we will jump into the electrophilic addition reactions, which are those that parallel the alkene reactions. And at this point, I'm going to try to just, in each lecture, I'm going to try to cover what is on our schedule. And I'll try to stick to that. So some lectures might be a little bit shorter and a little bit longer, or a little bit longer than the 50 minutes